I'm John Doran. I'd like to tell you a story. In Denver, Colorado, we have a old computer group called the 6502 group. It's been in existence since the 1970s, and we still meet every week. And one of the members of the 6502 group is Eric Smith, whom you know. If we go back in time to the beginning of the Pleistocene, 2008, Eric and Richard Otteson, another of the 6502 group members, were building handheld RPN calculators based on the HP model. They were using a PIC processor to implement the code, and they used little tactile switches for their keyboard and a what they call a smart liquid crystal display module. I bought one of those little calculators from Rich. I'm sorry I didn't bring it, so I can't show it to you. But doggone it, I wanted Nixie tubes. I mean, the liquid crystal display dominates today for several reasons, perhaps foremost among them. The power requirements are almost negligible, so it's perfect for handheld, battery-operated devices like calculators.
What portability index is that?
High enough that I don't think we'll pass it around. Anyhow, so I had a harebrained idea, really ridiculous, that what I would do is I would take Eric and Rich's calculator design and then discard the LCD display and then build my own module with Nixie tubes and neon lamps to perform that function. Instead, what I was going to do is use a second PIC to decode their display instructions and then make it happen on my little module. So I went so far as to build a perf board wire wrap prototype, and I actually designed and built the keyboards, and for whatever reason, other problems intervening, I guess, I just decided to let that slide. Nixie tubes, incidentally, are they were among the first displays used in small calculators, but they just...
What year?
What year of what? I'll get there. Nixie tubes were used in some of the earliest calculators, like the Sumlock Anita calculator, which had the keyboard from hell on it, and some of the Wang calculators, but they're not very good for small portable devices, but they're large. The Nixie tube stands a good inch high. They consume a lot of power. For example, in these units, each digit dissipates about half a watt. And they run on high voltages. Yeah, not really satisfactory for use in portable devices, but for a desk calculator, we can live with these things. They're also very expensive. And the 1960s were the heyday of the Nixie tube, and they were widely used as instrument displays by Hewlett-Packard. The tube itself cost between $5 and $20 a digit, and that's in 1965 dollars. But
What year again?
in the 60s were the heyday. They were invented in the late 50s. It turns out that the Russians loved Nixie tubes, and they made them and their IC drivers all the way up until the 1980s. So they're plentifully available and relatively inexpensive. Okay, we move up in time to the year 2023. And I was showing Eric a bunch of my junk down in the basement. I showed him the calculator keyboards, and Eric suggested that we go ahead and complete this Nixie calculator. He recommended that we, instead of putting our own PIC on our own board and doing it that way, just use a commercially available processor board, like a Raspberry Pi on our Arduino, which weren't really available in 2008, and use a and then use that to send data serially to a display module based on our Nixie tubes and neon lamps. So we got a processor board with a RISC-V on it. Eric programmed it, and we went ahead and built them into these units. We discovered some interesting things.
You're aware of the HPCalc display?
Negative.
Huh?
Not familiar with the HPCalc.
In the early 70s, so your statement was correct. Jim Carter, who owned HPCalc, had a partner who did exactly what you're doing this, except what they did is they took a standard HP calculator and they mounted it on a board so the teacher could stand on the podium and have the display out, the calculator there, and use it as a teaching aid. And they made it for, I don't remember how many different models, at least 3 or 4 models of HP calculators.
Okay, thank you. We discovered a few things when we designed these units. First of all, we're working with a technology that really hasn't been in common use for decades. I know certain devices like Nixie clocks are pretty popular right now, and you saw Jeff Quickshaw's Nixie watch. But in general, not too many engineers are all that familiar with how these devices work. And if you ask anybody what voltage a Nixie tube runs on, you'll almost inevitably hear 170 volts.
Right.
That was, in fact, the minimum. And Burroughs, the manufacturer of the tubes, recommended that for better uniformity and performance, you should operate it on the highest practicable power voltage, and then you just use a larger anode resistor to limit current. So when we first designed this, I went with 180 volts, and we found that the commercial integrated drivers for the Nixie tube, like the TI 74141 and the Soviet equivalent, it's a Kilo 155 India Delta 1, had output transistors that would break down. You turn the thing on and you just see this fuzz in your Nixie tube instead of the desired digit. And we did a little experimenting and found that cotton picking driver transistors in the chip break down at 60 volts, and that's not going to work with 180. So we lowered our voltage to 170, like they say, and found that that worked reliably. The Russian part's actually said to be better than the TI because it has lower leakage. And when you break down those output transistors, usually the chip isn't damaged at all because your anode resistor limits the current sufficiently to protect it. But even the Russian parts are going to get harder and harder to get. So if you ever want to build a Nixie calculator, you might consider one of the new chips just become available from Microchip. They have a shift register IC with 32 bits with high voltage outputs capable of withstanding over 100 volts. And you could use that chip, eliminate both the decoder, BCD to decimal decoder, and drive that directly. And that'd probably be a good way to do this thing going forward. You'd get a simpler board design. So these units here, we built the system unit into a enclosure with a little yoke here so you can adjust the viewing angle. And then we've connected it using a cable to our keyboard here. And you're all going to be free here in a few moments just to file up and take a look at this thing. One of the things we did was to try to select components and materials and everything so that it's easy to build. And I think one of the emphases I'd like to make on the design of this unit is we were in love with Nixie tubes, so we used Nixie tubes. But the point is the approach we've taken allows you to go with whatever kind of display you prefer. Eric is fond of a digital display that uses mechanical flaps. There are vacuum fluorescent displays, pneumatron displays, you name it. If one of those things appeals to you, then it's really easy to take our design, just substitute those for the Nixie tube. So I think now I'm going to go ahead and turn things over to Eric Smith. He'll talk a little bit about the implementation of the code.
So you all are aware that I've been writing calculator simulation code for years. Nonpareil is the most recent stuff that I've released, and I'm actually in the process of rewriting that because I've built up a lot of technical debt and want to improve it. So this calculator uses a much simplified version of code out of Nonpareil to emulate the processor used in the Woodstock and Spice generation calculators. Those use different chips, but it's the same architecture. And so I ripped the simulation code for that out of Nonpareil and wrote new code to drive the display and keyboard. So arguably my contribution to the project is relatively minimal. I did work a little bit with John on defining how the display board was going to work. So unfortunately, if you saw the listing on the website of what the talk was going to be, the title got changed in the agenda because no one knew that the specific title I had, "You can build an RPN calculator from the things you have at home," parenthesized, if you're an electronics nerd, is an allusion to the lyrics of a Bill Sutton folk song, which I recommend, "Do It Yourself," which says, "You can build a mainframe from the things you have at home." So if you're interested, Google or YouTube look up for Bill Sutton and "Do It Yourself." So I started writing the simulation that became Nonpareil back in '95 and have evolved it quite a bit over the years. It's been relatively inactive for the last, well, pretty much a decade. I picked it up and started working on it again recently. And so, yeah, when John and I started talking about actually finishing his Nixie tube calculator, then that was the obvious thing that came to mind, as well as use a newer code base rather than what Rich Otteson and I had used back in the aughts. You know, back then we used character LCD modules, and you know, Rich Otteson only joined us at the conference once, but you know, we've showed off those early calculator prototypes we've built. So John started designing. He'd already developed the keyboard PCB, which is actually very simple. It's just a scanned matrix, 5 by 7 keys. And that's using Cherry MX key switches like you would use on a mechanical keyboard. But as you see, it doesn't use typical keyboard keycaps. John had found these flat, relegendable keycaps that fit Cherry MX key stems, made by PI Engineering. And they're not cheap, and of course Cherry MX switches aren't cheap, so it's a relatively expensive keyboard, but works really nicely. And as John said, you'll all have a chance to try it out later. So John wanted a basic but functional scientific calculator, and he had chosen, actually before we started on the Nixie, before we started collaborating on it, he had already chosen that he liked the HP-32E, which is of course a non-programmable scientific. And with the Nonpareil code, I could have put any model in there, but so we started with the 32E. I'm gonna circulate. I mentioned the key legends, and what I did for the key legends is rather than you know, do them by hand, which John originally actually did his by hand on you know, a little piece of paper, cut and shoved under the top part of the keycap. We wanted a little bit nicer thing, and so rather than doing a sensible thing like just going into a graphics program like maybe CorelDRAW, which I don't have, or some open source equivalent, I decided, well, the thing to do is to write a C++ program that generated the key layout and output a PDF file. And actually, it actually outputs 3 PDF files, but of those, one goes to the printer, and then once it's printed, a second one goes to a Silhouette CNC cutter, which can cut paper and vinyl and such things, and cuts them out. So I'm going to circulate a sheet of the labels, most of which have not yet been peeled off the paper. And also, we printed some model number, et cetera, labels to put on the back of the system unit and of the keyboard. So I'll circulate these around. I would like them back later. So, yeah, we got the software running on it in May, and there's been very little change to the software since then due to some misadventures that I had. But it's basically functional, and John mentioned we're using a RISC-V microcontroller. It is a Chinese-made chip from, I won't try to pronounce their Chinese name, but they go by WCH in Latin. And it's a very inexpensive microcontroller, but fairly powerful. The eval board, we actually use the vendor's eval board in this rather than laying out our own board for the processor. And the eval board costs less than $10. So we had a bit of a misadventure with that it turns out they've gone through multiple revisions of the board, and they changed the connector pin out on that, which we were not initially aware of. And so when we had to change out the board on one of these because it was not working properly, then it didn't work at all because the connections were wrong. John said, oh, well, he could rewire the connector for the new pin out. And I said, well, let's try to get the old board working first. So we did recover the old board. So we have a few more boards of this revision, but other than that, in the future, we'll probably have to use the new one. The display, John mentioned the either TI or Russian driver chips. I think we're using all the Russian ones now. And what we have is basically a long chain of shift registers. I believe there are 74 HCT 594s, which is an 8-bit serial load shift register with a latch. And so to drive the display, we have to give 4 bits to each of those display drivers to display 1 digit because they're a BCD to decimal Nixie driver. And you'll also notice we have decimal points. There existed Nixie tubes that have decimal points, but they're really hard to find now. So what we have is neon bulbs for the decimals. And of course, any 2 neon bulbs are common as dirt and still inexpensive, but they're also a little bit large, and they're not designed to be viewed end on. They have the nipple of the tube at the top. But what John had found that's very interesting is what was known as an NE1H, and that is a smaller diameter tube, and the top of the tube is flat or maybe even slightly concave, and is deliberately intended to be a lens to make it better for view from the top. So that's what we used. John at one point had talked about just using LEDs for that, and I was shocked and horrified. And I said, you can't use LEDs in a Nixie calculator. Now, I didn't know that the NE1Hs were actually going to work out this well, and you might notice that they're a little brighter than the Nixies. We didn't readjust the current limiting for those because those run on a different strike voltage and different sustaining voltage than the Nixies themselves. So we might tweak that. We might tweak the resistor to equalize the display intensity, but they work pretty darn well. And Aside from the calculator, early on before we had the calculator running, I just wrote some simple programs just to do a keyboard test and then a display test. And those aren't very interesting, except insofar as the display test was useful because when you have even new old stock tubes, but certainly when you have used tubes, they may have cathode poisoning. So all the digits, what you're actually seeing glowing is the cathodes of the tube, and there's a separate one for each numeric character. And you'll notice that this technology, the different digits in one tube are at different depths. So, if it's a 3, it's a different depth than if it's an 8, and et cetera. They obviously are all different depths. And this, by the way, if you ever watch the movie Monsters, Inc., the Pixar movie, the displays in the animated film on all the Monster Universe high-tech equipment are Nixie tubes. And they actually did the differing depth effect. So obviously, Pixar employs a lot of nerds, and some of those nerds obviously really like Nixie tubes. And I mean, who wouldn't? They're very cool. So I was going to mention some firmware limitations. Ultimately, I threw together that firmware very, very quickly, and so it works. It could probably work better. The keyboard scanning that's in there currently is very crude, so it's possible it could miss an occasional keystroke. Forgive me for that if that happens when you're trying it. We intended to bring out the USB that is used to load the firmware to an external connector. We have not done that yet. So at the moment, you have to totally disassemble the thing if you want to reflash it to upgrade the firmware or the like. What I want to do is put a bootloader in the flash so that you don't have to depend on the factory programming method, but we haven't done that. And if we want to do programmable calculators for the 20 or 30 series, then they typically use a slide switch for program versus run mode, or I think some calculators use a slide switch for degree mode or that sort of thing. So obviously there's enough space on those keyboard boxes that we could add a rocker or a slide switch for such a thing, but we have not done that yet. So I definitely want to get other calculator models simulated in the future, and one of the ideas is that we could actually just build different keyboard boxes for different calculators, and we could actually have the keyboard self-identify and tell the main unit, oh well, I'm a 29C keyboard, and have the main unit able to simulate whatever calculator you want just based on what keyboard you plug in. So as John mentioned, we are thinking about building some more system units that use different displays. He described it as being very simple to adapt the design to other displays, and being fundamentally a software person, I might challenge that assertion slightly. It wouldn't be entirely trivial, but I mean, any moderately proficient hobbyist that knows electronic design could certainly do that. And so,
for him if you do it,
or vice versa, yeah. So I hope in the future to display additional calculators that use different display technologies. Are there? That's about it. Are there any questions?
unit cost?
I'll let John answer that.
Yeah, and I have a couple things to tell you about packaging. We didn't really track the cost, so I can't tell you for certain, but certainly several $100s. The Nixie tubes that I'm using here have been in my junk box for 30 years or more. And so if you have to go buy those, they're going to cost a little bit more.
It's difficult to get these. You ideally would like all of your tubes to match, but we sucked up the last ones that we knew of a source that had a bunch. And so as far as I know, the only way to get these particular tubes at this point is to buy them onesie, twosie, or maybe sets of 6 on eBay, which is a bit unfortunate.
You know, this is a Burroughs model of 5991 Nixie tube and used for instrument displays. The Russians have one called the India November 12, which has the same form factor and plugs into the same socket. Unfortunately, they were lazy, and they used the cathode for a number 2, turned it upside down for their 5. I don't like the looks of it at all. Some people don't mind. Any other questions? Yes, sir.
I used to come across a lot of old test equipment that had Nixie tube displays, like the HP-5440 voltmeter. I'm wondering how feasible would it be to take one of those things apart, use the Nixie tubes and the drivers out of those for projects like this? Anybody ever consider that?
I'm sure that you could. The HP, for their 5245L frequency counter, used this tube and a little module with a decoder and driver. You could take that thing directly, supply power to it, and run it. I don't see any problem.
Is it, I've never looked, but is that just a BCD input into each module?
I believe that it is, yes. And you'll notice they also have special tubes for displaying your exponent or your plus and minus.
My code is not currently using the plus,
Yeah.
which is actually a separate cathode from the module, because the original
Hang on.
HP calculators didn't display plus. John and I disagreed over whether plus should be displayed.
Yeah, I'd like to say plus, but he said, well, that's just clutter.
It's an option in the source code. We can turn that on.
Okay.
What's the driving voltage for the tube?
These Nixie tubes are running on ahead 170 volts.
No, I mean the input, the driver.
Well, the decoder driver is TTL, so TTL level signal. And Joey?
Yeah, could you explain again about the cathode poisoning?
Okay. There are any tube, not just Nixie tube, but anything that has an electrode like this that emits electrons. If contaminants build up on it, for example, or even if it just wears out, in the case of an ordinary vacuum tube, the thing will cease to function, and the behavior is as though a really large series resistor were in the circuit. And Nixie tubes are a little less prone to that than conventional hard vacuum tubes, but it's still an issue. I have one tube in mind that you may notice one of the tiny portion of one of the digits isn't lit up. Yes, sir.
You know, failure on these is corrosion on the pins as it creeps up to the glass seal.
Yeah, that's not generally a big problem because when you insert it in the socket, it cleans the pins off.
It is when you find it in the garbage dump, just
Yeah.
before it's being dumped out. They just save our time. You're done.
Okay, I'm sorry, they tell me I have run out of time. But feel free when you get an opportunity, come up and paw these things over.